Let's review constant pressure or coffee cup calorimetry. We assume that no heat is exchanged between the system and surroundings, only between system components. The heat gained is equal to the opposite of the heat lost, or the heat lost is equal to the opposite of the heat gained. Either form of this equation is perfectly good. We recall the two forms of the equation whenever heat is being transferred, either within a given state of matter, in which case the delta T form, that is the one on the left, is applicable, or when there's a state of matter transition, we use the form on the right, where we have to choose the positive or negative sign, and then we have to know, is the heat of fusion applicable or the heat of vaporization. We would use the heat of fusion if we're doing a solid-liquid phase transition. We would use the heat of vaporization if we're doing a liquid-gas transition. 25.2 grams of ice at negative 8 degrees Celsius are dropped into 215 grams of 93.5 degrees Celsius vegetable oil. The oil's specific heat is 1.67 joules per gram Kelvin. The constants for water are shown at right. Find the system's final temperature. We're going to have heat lost and heat gained. Who's going to lose heat? Who's going to gain heat? I think the water is first going to melt and then warm up, and the oil is going to cool down. So the oil is going to lose heat and the water is going to gain heat. We want to put an arrow pointing to that negative sign so that we don't forget it. Here are the forms of the equation down in the lower left, just so we don't forget those. The oil is going to cool down from 93.5 degrees Celsius to something else. And we're going to assume that the oil is going to remain a liquid because we're only given the specific heat of the oil. We've got the mass of the oil, 215. There's its specific heat. And then the delta T will be T final, which we don't know, minus T initial. T initial is 93.5. What about on the water side? We first will need to heat the ice, and then we'll need to melt it, and then most likely we're going to have to heat the water up somewhat to reach the final temperature, which of course will agree with that of the oil. To heat the ice, we're going to use the delta T form of the equation. There's the mass of the water. There's the specific heat of ice, which we picked from the constants here in the upper right. And then the final temperature after heating ice is of course just going to be 0. 0 minus T initial, which is negative 8. Then we're going to melt the ice. To melt the ice, we're going to use the non-delta T form of the equation. That is, we're going to use this one in the very lower left corner, m C sub f. C sub f here is 333 joules per gram. And then we're going to heat up that water to its final temperature. There's the amount of water, there's the specific heat of liquid water, and then delta T is T final minus T initial, and of course T initial for this portion is 0. If we combine all of these and set it equal to what's written on the right, then solve for T sub f, we should be done. When we heat the ice, it takes about 418.72 joules to do that. To melt the ice takes 8,391.6 joules, and then to heat the water, we've simplified as best we can 105.34 T sub f. On the right, we've used the distributive property negative 215 times 1.67 times T sub f gives us negative 359.05 T sub f. Then we've gone negative 215 times 1.67 times negative 93.5. Of course, that's going to give us a positive number, 33,000 and change. If we combine the terms, we get 464.39 T sub f on the left side, and on the right side we get very nearly 25,000 divide both sides by the 464 number, and sure enough we do find that water ends up in the liquid phase.